You still hear me? I was wondering, do we start at 3? Is that?
No, we start now.
Oh yeah, okay. So good afternoon and welcome to my session that I'm going to be delivering on reinforcement learning in gaming. My name's Alan Smith and I work for Active Solution based in Stockholm, Sweden. I'm just going to see if I can get the PowerPoint running on the correct monitor, excuse me. That's better. And I'll be delivering this session on reinforcement learning and gaming together with Eva Padri. From my perspective, this is focusing on what I define as hobby projects, which is, when I've got some free time, I like to learn about artificial intelligence and machine learning. I also like working with gaming, and I find it a challenge to use the kind of environments that we have within computer games as a model for being able to work with machine learning. So basically training an algorithm to be able to play a game and basically understand and explore the rules for the game. A bit about myself. My name is Alan Smith. I'm based in Stockholm, Sweden, originally from the north of England. I describe myself as a developer, trainer, mentor, and evangelist. I'm most happy working in Visual Studio, writing code. I also deliver quite a lot of training courses focusing on Microsoft Azure technologies and more recently focusing on some of the services that we've got on the AI platform. When I'm not delivering training courses, I usually work as a mentor in projects and to help development teams to be able to build up their skills working with cloud-based technologies. I also describe myself as a bit of an evangelist in that I like to look at new technologies and I like to encourage others also to focus on looking at these new technologies. I've been an MVP for probably about 15 years and I'm currently an Azure MVP. And I like to have a strong involvement with the community. I've been involved in the Cloud Burst Conference, the AI Burst Conference, which is events that we've been running in Stockholm. I've also been involved with the Global Azure Bootcamp and Global AI Bootcamp. And I also try to speak at many conferences, as many as I can. I also host a YouTube channel at youtube.com/user/cloudcasts, and there I basically share some of the ideas and experimentations that I've been doing with the Microsoft AI technologies. So what we're going to be looking at in this session is the concept of reinforcement learning in gaming. And one of the first projects that I started out with was looking at driving games and trying to understand how we can, look at the physics model that we've got in a driving game, and then be able to generate an artificial intelligence algorithm that's going to learn how to steer a car around a track. Now, when I first saw this as a challenge, I thought this was some kind of magic that was going on. I really couldn't understand as a traditional developer how all of the rules would work for being able to govern, what decisions a car would make as it's steering around a track. I then started to look at machine learning and started to read the basics on various concepts in machine learning, and was introduced to a technique called supervised learning. The idea of supervised learning is that we're going to be training a machine learning algorithm to come out with a set of rules. And what we're going to be supplying the algorithm with is the data and the answers. So supposing you're trying to predict the price of an apartment, and what you do with supervised learning is go and find as much data as you can about apartments that have previously sold in your area or in the area that you're wanting to investigate. You get as much statistics about these as possible. How big are the apartments, how many rooms do the apartments have, when were the apartments built, when was the kitchen refurbished, what type of area it is, do you have a view of a lake outside the apartment, is there good parking, is there a good bus stop, is there a good train station, and so on. And based on all of that data, you would also have the price that these apartments sold for. And what you can do then is you feed all of that information into a machine learning algorithm. And you basically choose what type of algorithm you wanted to use. And the algorithm would come up with a set of rules. Now, when you've got this set of rules, you can basically feed in your own data. For an apartment, you want to know how much it should cost. You basically feed in the size, the location, what level it's on, if it's close to a train station, and so on. And based on the rules that the algorithm has generated, it will basically predict a price. It will come out with a prediction. When we look at reinforcement learning, how does a car learn how to drive around a track in an environment? We don't actually have, a set of data to be able to, understand, what is a good lap, what is a good way to drive a lap, what is a bad way to drive a lap. You could do supervised learning by, recording the inputs that a human driver makes as they drive around the track, and then trying to train an artificial intelligence to basically, do what a human would do in this particular situation. But with reinforcement learning, we like to start with a completely empty slate. We don't really know anything about the particular environment, and we're going to train an algorithm to explore that environment. Now, the environment can be anything. It could be a driving game. It could be, a simple physics model. It could be an equation, just something that we can explore and simulate inside a computer. The environment has to provide a state. So if it is, a lunar lander game, the state will be, how far you are above the ground, how much fuel you've got left, how fast you are traveling, and various things like that. Maybe the weight of your spacecraft. That's going to be the actual state of the environment. We can also take actions in the environment. When you're playing a game, you're going to be, inputting the controls. What control am I going to use to make a certain action within the game? And we also have to have some kind of way of rewarding the actual player for being able to perform certain actions and be able to get certain actions right. Now, in the driving game, my reward is how far have you driven down the track without crashing. And then once the AI learns to drive around the track, you can start to look at the speed and say how fast you can drive around the track. With a lunar lander game, maybe the reward is going to be what's the actual landing speed when you land. You're going to start out by crashing. The AI doesn't really know anything, but if you can reduce the speed at which you crash at, eventually that's going to be a successful landing. So the environment, the algorithms that we're going to be training, or the kind of simulation, the pieces of code that are going to be running in the environment, we describe these as agents. And the agents we're going to feed in the state, and the agent is going to come out with an action. So we feed in all of the properties about the lunar lander. The agent decides to thrust the engines, for example, and that's going to result in a reward coming out, a change in the actual environment, and then we can give the reward back to the agent, which is kind of a measure of how well they performed. And we run this with a large number of agents for a large number of iterations, and hopefully the agents should become better at being able to negotiate that environment. And we should see that generally the average reward and the maximum reward over time is going to increase and get better. Another way of thinking this is the infinite monkey theorem. If you take an infinite number of monkeys and put them in front of an infinite number of typewriters, eventually one of them will write the complete works of Shakespeare. The others will just write regular expressions. And this concept talks about also a genetic evolution. If we basically have these monkeys banging away on the typewriters, eventually we're going to find ones that are getting closer to writing Shakespeare. So we use genetics and we basically crossbreed the monkeys that are better at writing. And eventually we should be able to crossbreed these monkeys together and get a monkey that can write Shakespeare. At least that's kind of how the theory of evolution goes. Now, we're going to be simulating the evolutionary principles in an algorithm which is known as a genetic algorithm. They've been around for a long time, I think since the 70s. There's a big old book on genetic algorithms that you can buy if you want to go through all of the theory of how genetic algorithms work. And there's various different ways of being able to implement them. I've built them in C# and I've built them in Python. Now, compared with building something like a neural network, genetic algorithms tend to be very simple to implement. Any programmer can create one. We start out with an initial population, and in this case, we've got just 5 members in this population. You may have 50, you may have 100 or 200. Typically, that's the kind of number that you'll have in a real population. And these are basically known as the agents that are going to be exploring our environment. The next thing we have to do is we have to evaluate the population. So the initial population is very often generated with random numbers. We use a random number generator to set all of the actual parameters in the initial population so that they're completely random. And then we let them all loose in the environment. And because they've all got random parameters, Some of them will perform better than others within the environment. They'll all be completely hopeless. They'll all crash and burn. They won't be able to, get anywhere near saving the game. But some of them, based on the evaluation, based on the actual score, will do better than others. So what we do is we perform a period of selection where we basically sort all of the agents within the population based on their score, based on how they performed within that particular environment. So here we've selected the top two, number 1 and 2, the red one and the orange one, that have performed best. Then we perform something called crossover. So typically there's going to be quite a few of these numbers that we're using. They're usually floating point numbers that we use to actually set the various properties within each of these agents. And maybe say there's 10 floating point numbers. What we'll do is we'll randomly pick some of the numbers from the top performing one with some of the numbers from the second performing one. We do it in reality. We've got 50 in the generation, so we'll have a larger number. But what we're doing is you can kind of think of these numbers as being genes within a piece of DNA. We're basically doing a crossover and selecting numbers from the top performing ones to actually form the next generation. So here we've got 5 members in the next generation, but their numbers that have been set within their actual agent are basically based on the numbers from the most successful members of the first generation. We then do something called mutation. There may be numbers that needs to be in the equation to perform well, but we don't have them in the initial population. So what we do is we use randomness again to actually just flip some of the numbers, and just we usually use about 1% or something, or around about 1%, and we just set those to completely new random numbers to induce some kind of a more randomness or mutation in the population. And that's going to create the actual second generation number 2. And then we go through the stages again. We do the evaluation, the selection, the crossover, and the mutation, and that produces generation number 3. So we keep running round this until what usually happens when we're running the genetic algorithms is we kind of reach an actual peak. We see the learning curves going up quite steep initially, and the learning curves tend to flatten off when it tends to kind of reach the limits within that particular environment. They can sometimes jump up more and progress more, but generally that they will progress after maybe 100 generations to have actually explored that environment and found what the algorithm considers to be an optimal solution. So looking at doing this with rockets, I was kind of really inspired when I was building this. It was just about the time as Elon Musk was launching Falcon Heavy, and I watched that first rocket launch with my daughter, and we were just amazed by seeing these 2 booster rockets coming down simultaneously, landing on the launch pad. I liked physics at school, so I was really interested in they must have done some really smart physics to be able to get that to work. So I originally built this demo basically inspired by that, to see if a genetic algorithm can land not just 2 rockets, but 25 rockets simultaneously. So I came up with this concept, something called a thrust vector table. And what this is going to govern is the amount of thrust that the rocket uses based on the actual altitude. So if it's 1 meter above the ground, it will use certain thrust, 2 meters above, a certain number of thrust, 4 meters, 8 meters, 16 meters. And there's going to be a certain percentage of thrust that the rocket used. So what I did was I create 25 of these rockets. The thrust, what I call the thrust vector tables, are completely random, meaning they've just got completely random numbers, and we basically put them into an environment. We basically drop them from a certain height and see if they can land successfully. They all pretty much in the first generation, they all hit the ground and explode, but some of them hit the ground slightly slower than other ones. So we select the ones that crash the slowest. We do the simulation of the rocket landing. We select the ones with the lowest landing velocity. We then perform the actual crossover to generate 25 new thrust vector tables, and then just add a few random numbers into these thrust vector tables, so that they basically have a bit of randomness in them, and the generation progresses. And then we run this a number of times. We keep running around this loop until we do get hopefully the rockets landing successfully. Okay, I'm gonna look at this and run into the demo. What we're measuring here, I'm actually running this in an application called Unity, which has a nice 3D engine and also a great physics engine that we can use for the simulation. It's also quite good at creating explosions as well, which is good fun. And what we have the speed of the rockets, we have the altitude of the rockets, and I've also, in the physics model for the rockets, given them a certain amount of fuel. So as they use their rocket boosters, the fuel decreases, and that decreases the mass of the rocket, so they get lighter as they burn off more fuel. Also, if they use too much of their boosters, they will actually run out of fuel and come down and crash. So there's also that equation that we have to take out, and the output from the rocket is the actual amount of thrust that they are making. Okay, what we're timing them on is the actual landing speed. We measure the landing speed, and that's the reward that we use for our particular environment to be able to drive the genetic algorithm and to be able to perform the scoring and the selection. Okay, so landing rockets with a genetic algorithm, what could possibly go wrong? So this is the simulation that I built. I think it's one of the first genetic algorithms that I implemented. So if I start this thing going, we should see 25 rockets coming down. As you can see, the thrust vector tables are completely random, and we get a big cloud of smoke and lots of flames. So this is the second generation that will hopefully have learned a bit more successfully, but they all crashed as well. And here comes the third generation. And again, they're not too successful. Usually one of the rockets at least has landed by now. So because they're random numbers, you can have a bad rocket day and you just end up with lots and lots of explosions. But we're going to persevere. We have time, and hopefully we will actually see some success in this algorithm. They do seem to be crashing slightly slower as they're running through the actual algorithm. Okay, so as I mentioned, this is at Unity. You can pick it up as a free download, and it's fairly easy to code with. The actual code is written in C# that I'm using for the simulation, and there is a Visual Studio plugin to get this to work. I'm going to restart this again, I think, because sometimes you get like the series of random numbers is pretty bad, and because of that, it just takes a long time to evolve, and just creating a complete new generation with a completely new random numbers is hopefully going to be more successful. They do seem to be spread out a bit more than previously. And they're just crashing again. Okay, well, we'll give this another couple of minutes. We can't spend an hour or half an hour watching rockets crash. But I think one landed, two landed, so that's a success. So hopefully, now that some of them have figured out to land, those actual genes will propagate through the generation, and we'll start to see that we've got a higher success percentage of these rockets landed. So we've got 5 of them landing now. And now we've got about 10 of them landing, so it does seem to be evolving. And now it does seem to be getting a bit more successful as we're progressing through the generations. As I mentioned, usually second or third generation, you do get a successful landing, and that will quite quickly propagate out into the rest of the population. And as it's running through these generations, the successful genes are basically becoming more dominant within the population, and hopefully that will basically eradicate the thrust vector tables that are causing crashing. However, we always do have a bit of mutation in here, so it is always generating a few random numbers. We think we just got one crashing there, so let's just see if we can get a full generation landing. There's always one that has this random mutation in and will crash, but we're getting close. One last go and see if we get it successfully this time. No. And that one, as I mentioned, we're putting random numbers in, so it will actually occasionally it will just give one a crazy thrust vector table that does something a bit wild. So Unity is a nice environment for playing around with AI. They do actually have their own artificial intelligence functionality baked into Unity. I've not really had a chance to explore it too much, but it is there if you want to do and explore AI using the Unity physics engine. Now, I'm going to talk about state, and this varies based on the actual environment that you are trying to simulate. I've mentioned lunar landers before, and here we've got floating point numbers as the state, or maybe integer numbers in this case, where we've got the altitude, horizontal and vertical speed, we've got the number of fuel, the number of time that we are in, and the actual score. This is a nice thing that we can actually use to actually provide the feedback, the actual reward from the. There's also been a lot of work done on these games. These are from, I think it's an Atari 2600, 2600, which was a really early console game. I remember these when I was about 10, 11 years old. The early Atari games, and you got a cartridge that you could plug in. So they had these kind of simple arcade games that were all bitmapped at fairly resolution. And in these types of Atari games, what we actually use for the state of the actual environment is the pixels present on the game. Now, you could build it based on variables in the game. So you've got the position of the Pac-Man, the position of the ghosts, and you've got variables where all of the dots are. But by using the actual bitmaps of the screen, the actual algorithm can be completely generic. So you feed in Pac-Man, and it can basically understand the pixels of the screen on Pac-Man. And then you give it Space Invaders, and it understands the pixels of the screen on Space Invaders. The reward is really easy. We've got a score, which is numeric. So the higher the score, the better the agent will have performed in that particular algorithm. And we can use that as an easy way to be able to run that. And if you're working with OpenAI Gym, you can actually run simulations of this. I think you can also do it in Azure machine learning. Maybe Eve can sort of clarify this, but it's one of the simulations that we can now run. As games get modern, this is Forza Apex, I think, which is from a couple of years ago. You can see that the actual state of the game is really complex. It's going to be, high resolution game. It's going to be really challenging to use the pixels on the screen here. Also, we've got a lot of noise in here. You can see that we've got the car, we've got the actual, the pictures of the road. We've also got this kind of a sun flare coming off the car and all of this stuff. So lots of the actual graphics is just, eye candy on the game to make it look nice. And it's maybe not relevant to the game. So here, it can be challenging for the AI to understand if it should go straight down this road or if it should turn. We understand that there's some road cones here that mean that we've got to turn. So what I do when I'm working with these types of games is I've actually processed the frame to be able to extract the kind of a driver line here. Now, if you're a racing game enthusiast, using a driver line is cheating really. But what this allows us to do is to apply a color filter to the actual inbound image that we're getting for the game. And what we get out of that color filter is a bitmap that looks like this. Now, this is a nice bitmap. It's low resolution. I can feed it into a neural network. And the information here is just the information we need to know, or that the AI needs to know to be able to negotiate the corner. We're basically bringing out that actual corner there. So this is what I did in the state on this game. I also experimented a bit with the custom vision service in Azure. So what you can do is you can train a model to be able to recognize cars. It's a convolutional neural network. And it's fairly easy to go in and upload a bunch of images and train this particular model. So it basically understands, that this is a car and this is a car. It ignores the area where your driver car is. It doesn't want to detect this as a car. This is basically the actual player. So I was thinking, maybe this could help to avoid other cars in the driving game. Otherwise, if you're just following the driving line, then you're basically going to keep crashing into other cars. It won't understand the concept of other cars, and you've got to avoid them, and if possible, overtake them. The action that we take, again, is going to be dependent on the environment. In some games, it can be simulating a key press. In the Atari simulation games, we've basically got this old Atari joystick. I used to have one of these years and years ago in my VIC-20. And so you've got up, down, left, right, and fire. Fairly simple inputs. With the driving games, it's really a floating point variable that you're using for the steering to right or left. The reward in the driving game, I was specifying the number of meters that you drive before you hit an obstacle. And what I was doing was basically, measuring from the actual statistics that were coming back from the driving game, how far we've actually driven. I think I took the speed and did a calculation with the time to actually figure out how far the actual car had driven. For the rockets, it could be based on the landing velocity, and for the actual Pac-Man game or the Space Invaders game, we're actually using the score, which we've got down at the bottom there. So looking at the driving game example and the state, the input that I was providing, as I mentioned, is the steering, and we were getting out this state looking like that. So I'm going to see if I can pull up the actual video, the outbound video for this, and basically show you how the driving game evolved. I have the video somewhere, if I can just locate it. Okay, so this is the actual evolution that I ran. It took probably about 4 days of evolution to get this far. I'll just whiz back to the first generations, and what's in common with the rockets is that you know, this thing basically didn't know how to drive. It just crashed, and that happened for a number of hours. Eventually it figured out that driving along the line and using the driving line as an actual guide could actually work successfully, and when it got to the road turning right, it turned left. So eventually it learned that you know, turning left wasn't a good idea, and eventually we managed to get it to turn right and follow this particular curve. So this, what I'm doing here, is just basically giving you the best bits, the kind of milestones in the evolution that this Lamborghini made driving. It's actually driving around the Top Gear test track in the UK. And it did actually manage to steer along the track. I could get it to kind of follow a straight piece of track. What I didn't get it to do, if we sort of go towards the end, was actually to understand that it should drive around this corner. I suppose if I left it running for a lot longer, it would have been able to figure that out. But it wasn't too great at being able to actually you know, get around that corner. I needed to play around with the algorithm. The challenge for me was it was taking like 4 days to get this far. You can't run multiple agents at once. You just basically have to run one agent and then restart the game and run an agent. So it took about an hour to get through a generation of like 50 cars and explore those. So that wasn't too successful. Another thing that can happen is we've got the concept of what's known as a false minimum, and this is on another driving simulation. What happened was, in the first generation, the most successful car, just by the random numbers that I was using, figured out that driving backwards, or basically because they're all set up as random, the car that basically started driving backwards basically got the highest score. So that car then went on to form the you know, the best car in the next generation. So we got the next generation of most of the cars driving backwards and becoming more successful. So this basically evolved to drive backwards around the track. It's not the fastest way to drive around the track, but it's what's known in AI as a false minimum, where the algorithm basically learns that, you know, this is the best way to do things, and it just keeps, you know, through reinforcement learning, doing the same thing and being able to you know, not being able to, you know, find an optimal solution. Something that we should try and avoid in machine learning. I've got a simpler example of driving games here that I can bring up. This is again something that I built really early on, which is a 2D physics engine, where I was using artificial intelligence and machine learning to navigate basically a 2D world. So I'm going to bring up the actual screenshot of this. I'm just starting the application up in Visual Studio. And what we've got here is a generation. I think there's 50 cars in each generation. And what they're doing is attempting to drive around this track here. They're powered by a neural network. What I'm doing is I'm basically using distance sensors, or simulated distance sensors, that tells you how far the edge of the track is. You know, straightforward angle, 90 degrees angles, and 45 degrees angles, and that's fed into a neural network. And we're using the numbers in the neural network as the actual numbers in our genetic algorithm. So it will take the most successful car, and it will basically use that as the basis for the next generation. So generation 1 got 493 pixels, generation 2 has got 578 pixels. And again, it seems to be a bit stuck, but it should actually, hopefully, learn to navigate around the track and be able to perform better. It's looking like that car has actually got a bit further than previously. Yeah, does seem to be making good progress, and it's hit the wall. So we got a good increase there. That got 1,000 pixels, and now hopefully we should be able to get cars that can, explore the environment more. You can see that the ones that were driving fast have been weeded out. So this one here that is going very cautiously. Maybe we'll actually learn a bit more about driving. No, it's got stuck there. Again, you leave this thing running through the generations, it does actually evolve and learn how to drive around the track. It does seem to be a bit stuck now. Maybe it did make a slight increase there. Looks like it got a bit further, the one that crashed here. No. So I'm going to leave that thing running, and I'll drop back to that a bit later on. This was when I was teaching a course up in Kista in the north of Sweden. They had an AI day, and the self-driving cars. This is basically a self-driving road sweeper that they've got, and this was another kind of a self-driving vehicle. The idea is that these things will be delivering our shopping in a few years, completely autonomous. There's not even room to put a driver in that particular vehicle. Another way that you can explore self-driving cars is the Carla simulator. So this is, again, it's free to download. There is a Python API that can connect to it. You've got APIs in other languages as well. But this gives you an environment where you can basically program the cars to move around the environment and access certain sensors. I've started doing a bit of work with Carla, but not got too far in the actual development of Carla. This again is displaying when the algorithms got stuck at a certain point. There was a tight bend at 733 meters on this track, so many cars were just getting stuck at this particular point in the track. That's just illustrating the actual self minimum option there. We did actually use this AI in the Global Azure Bootcamp racing game, where what we did was, this was the AI when the cars were driving backwards, another version of that. And the attendees at the Global Azure Bootcamp could choose if they wanted to go with, actually driving the game themselves or using an AI to actually drive the game. And the statistics came out, the actual scores. You can see at the top, the actual first driver in the actual scores was actually created by artificial intelligence from the actual Nigeria run. I used the Stig helmet from Top Gear for the human drivers, and then the Terminator skull for the AI drivers. So you can see that within the top 10, we've got 3 drivers in the artificial intelligence that are driving using the AIs. So they've basically evolved and learned how to drive around the track, basically faster than humans can within that particular game. So I'm going to hand that over to Eve now, who's going to basically look at the concepts of reinforcement learning and how we can run those in Azure machine learning. Just a quick flashback to this. We can see that this has now evolved, and several of the cars are now actually successfully completing the track. Okay, so I'm going to end my screen share if I can and hand over to Eve.
Thank you a lot, Alan. It was a really cool session, and I think it was really interesting to see all your projects that you have been working on, and it was really nice to see it. I'm really excited to share some insights with you and offer a first glimpse into how Ninja Theory's latest game, The Bleeding Edge, is allowing Microsoft to drive research into artificial agents that learn to collaborate with humans. Because Microsoft made an amazing history in machine learning and artificial intelligence, applying machine learning to improve many of their products and services, such as for the suggestions made in Office services. The approach of reinforcement learning became very popular in the recent years, since these game agents perform complex tasks really well, just like you have seen in Alan's session, and they're causing real breakthroughs in the field. There are many use cases in the world which uses this technology in the areas such as robotics, chemistry, education, and a lot more. So I'm Eve Party, Senior Analyst and Data Scientist at Avanade. I have been an AI MVP for a year now, and I am involved in different community activities. For example, I am part of the organizer team of the Machine Learning Conference and board member of the Global AI Community. And I'm co-owner of AI 42, which is a series of lectures for those who would like to become data scientists or AI engineers. And we aim to take attendees all the way from complete beginner to getting enough knowledge to be able to build their own model. I also write articles and often speak about my investigations and projects at meetups, conferences, or other community events too. And my aim is to save lives and support humanity with AI and data. It is important to make people feel safe while using intelligent applications and also make developers understand how they should control their solutions. We would be really, really happy to answer all your questions after the session. So please post your questions in the chat. And if you may be stuck somewhere while trying out the projects we show today, you can reach out to us. Also in the chat, maybe you can share with us which was your favorite demo. And you can find me on LinkedIn, Twitter, and Facebook too. And you can find my GitHub account as well. And yeah, let's go and continue with the topic. So the cool thing about the gaming situation is that the behavior of the agent is trained under the pressure of the game. Think of a character or a bot in a game, and it has to understand the state of the game, where are the players, and then based on this observation, so on the situation of the game, it should make a decision. For example, it could learn what to do when it's being attacked or how to behave in order to reach a specific goal. Microsoft proudly announced the preview of reinforcement learning on Azure Machine Learning at Build 2020. The new reinforcement learning support in Azure Machine Learning services provides scalability while training to CPU or GPU-enabled virtual machines with machine learning compute clusters that can automatically provision, manage, and scale these virtual machines. You can use single agent or multi-agent reinforcement learning for your training scenarios, and you can use different gaming environments, for example, the OpenAI Gym. You can build your models with TensorFlow and PyTorch deep learning frameworks, and it supports ONNX too. You can also track your experiments and monitor the runs, and Azure provides numerous AI solutions to build, run, and grow your games. So go on and accelerate your games with AI and machine learning to provide more realistic worlds and challenges for your players. To get started with reinforcement learning, you can check out the sample notebooks that you can find on this link to train an agent, for example, to navigate a lava maze in Minecraft using Azure Machine Learning, which uses single agent reinforcement learning. The goal of this agent is to reach the blue tile while navigating through this maze by walking only on solid tiles, and the agent might fall into the lava, in which case it has to start it over. And since the maps are generated randomly, the agent also has to learn how to generalize and adapt. The Project Paideia team has, so the Project Paideia team of Microsoft Research, in collaboration with game developer Ninja Theory, is exploring new opportunities created by reinforcement learning in the game Bleeding Edge. So the aim of the research is not to build an agent that is able to beat humans, just like the famous chess agent, but to collaborate with them. I would like to show you a game which is designed to rapidly test this collaboration. And you know, there are two players. I am the white players, and the trained reinforcement learning agent is the blue one. And we are locked in a room on a spaceship, and now we have to collaborate. So while one player keeps the switch active, the other one can go and press the buttons, opening up windows so the balls can fall in. And when the balls are down, then the door is opening and we can escape the room. Now, look what happens if, how do we collaborate when I, want to do something else? So the agent adapts. And if I say that I'm going to press this button for you, man, then he goes and presses the other ones. Or if I go and, go on the next one, that's already done actually. There. I don't want to go out on the door yet. I want to collide with you because that's funny. Yeah, but he tries to adapt based on what my moves are. So the Project Idea team wants to democratize state-of-the-art reinforcement learning techniques for any developer through Azure Machine Learning. And they would like to provide access to training infrastructure and easy integration tools as well. And by this, make developers able to apply reinforcement learning while building exciting games for the player. So in this session, we're going to use this situation. The blue circles are the agents, just like we've seen in the game I shown before, and they start spreading around and observe their environment while trying to find the landmarks that are shown as black circles. And they get rewarded if they find the landmarks without overlapping while spreading around. And for this, we're going to use OpenAI Gen's particle environment within Azure Machine Learning. Now, let's take a look into this example of how to develop with multiple agents using Azure Machine Learning in a simple gaming environment. Now, I'm heading over to my Azure portal, and to see this, you need an Azure subscription. Then you also need to generate a resource group and a machine learning workspace with a computation cluster in the resource group. So you can create a resource group just by saying create a new resource group. A resource group is just a container that holds related resources for an Azure solution. And it is a good idea to put in one resource group those resources that share the same life cycle, so you can easily deploy, update, and delete them as a group. So you can just create a new resource group, say, like give it a name. Yeah, this is a subscription that I shouldn't use for creating new resource groups, but yes, but this is it. So you create a resource group by giving it a name, then define where should it be, and that's all. Now, I already have a resource group, so that's fine. Now, let's create a new machine learning studio. You can just go to new, create, something like that, and then say machine learning, say create, and then you define which resource group should it be and give it a name. You should have a storage account, keyword, and app insights generated for you automatically, actually. And you should have a computer registry as well. And a computer registry should be used to register Docker images used in training and deployment. And to minimize costs, a new Azure Container Registry resource is created only after you build your first image. Okay, so when your resource is deployed, you can go to the resource and then you can launch the studio from here. This is the view that you first see when you launch your workspace. So you can choose to use notebooks to write your own code and build your own models and experiments. You can choose to work with automated machine learning, where you automatically train and tune your models. And you also get the best fitting algorithm for your specific scenario. And the designer is a drag and drop interface, with which you can prepare your data, train, and then deploy your model as well. Now, we should need compute as well, because this is where we are going to run our experiments. And if you can just go to new, you define that it should be a GPU. For reinforcement learning, it's a good idea to go with GPU, and you can go with the one that is recommended for you, or you can choose from all the other options, and you can just click next. But we don't create a new one now because I already have one. So I'm going to go to my notebooks. And this might look familiar for you if you have coded with Python before, where you possibly use the Jupyter IPython notebooks, which also have the similar folder structure and all the kernel and layout and all that. And what we first need, that is to create a files folder. And place there all the files that you can find in this GitHub folder. I'm going to share these links with you. But if you go to files, these are the Python files you will need to run this experiment. Now, when we are ready, we can go back to the main folder where you can create a new notebook and we can start coding. So, the cool thing about the notebooks that all the tools you might want to use are already installed for us. Still, you might want to update your environment, but then you are ready to use all the required libraries. Now, after updating the packages, let's return the machine learning SDK version, which is quite handy when you need to do some debugging. And it is a good idea also to define which Azure tenant you want to use in this code. And you can figure out the tenant ID if you go back to the Azure portal and go to tenant properties. Yeah, now it is time to connect to the workspace that you had just created, right? So you can use a predefined configuration with the use of this code, or you can specify it by defining the name of the workspace, the subscription ID, and the resource group where you put the workspace and the compute target. And you can find the subscription ID also on the Azure portal if you go to the subscriptions. And if the connection was successful, it will return the details of the workspace. The next step is to create a new experiment, which will enable us to monitor the run. And as parameters, we pass the workspace that we just connected to in the previous command, and we should specify a name for the experiment. Now, we also create a cluster where the training is going to run. First, we define the name of it. Then we are going to look around in the system, whether the cluster already exists. And if it is, it's going to say, yay, I found the cluster, so I'm going to use it. And if it exists, but stopped or not available, this code will return that information as well. Otherwise, if it's not generated yet, it will be done now. We should also specify the size and the number of nodes. And you can always change this code to use an existing cluster. And for that, you only need to change this variable here to the name of the cluster you want to use. And the good thing about this cluster is that it will scale down when it is not used. You're also welcome to increase the nodes if you plan to run more than one experiment on this cluster, but we can leave it as it is for now. So when the cluster is ready to use, this code will return the cluster created or that it found an existing cluster and it's going to use it. Now we are going to use a customized Docker image where all the necessary software and Python packages are installed, and the configuration for the training run is defined with the environment class. Since we also want videos to be captured, we want to see how the training is going, how well is it going, right? We want to capture videos and see how well our particles are moving around. So for that, we need to set the interpreter path 2, which is defining how big should be the video, how should it be coded, and so on. And for training, we are going to use the multi-agent deep deterministic policy gradient, or the MADDPG algorithm. And as the name suggests, it will be able to train many agents in the same time. And if the training runs over 3 hours, it will automatically stop. Similarly, if -400 reward is given. Then we have to initialize the reinforcement learning estimator with different parameters that are necessary for the training, the source directory with all the Python files that we added in the beginning, the entry script, and a scenario where we want to train our agents. We also defined the compute target, the training environment that we have created just a few steps before. And you're welcome to change the final reward parameter, but this code means that when it is reached, so when the -400 is reached by the agent, the training is over. The -400 actually is a pretty good result, but if you want it to be better, training might take longer. Finally, we also want to see some more information about the experiment while it's running. And a button is available to navigate you to the run details, which is gathered by this line of code. And if we go to take a look at the run details, I hope my experiment is still running because that's cooler to show when it's running. So yeah, my experiment is running. So I go to the child runs, open it up and see the outputs and logs tab, where we can find detailed information about each trial. So what does that mean? The training started, and it started from -500 as a reward. We have the time, we have the name of the trial, and after each iteration, after each trial, just like we've seen with the cars, so after each trial, we return what was the reward for that run. And the generated videos that we also wanted to have can be found here. And you can go ahead and download these videos, and then you can take a look how the agents behave. See, they are not that bad yet. Not bad anymore. They were like learning a bit already. All right, so instead of scrolling through and trying to understand the results just by looking at these numbers and the videos one by one, we can write some extra code to monitor each iteration of the training process. So we can also monitor the trials in runtime via TensorBoard. And this code should output this URL where you can find the dashboards. There we go. So you can see each iteration from the beginning. How is the rewards are changing? How are the rewards changing? And a lot of metrics are shown on these dashboards. It is really useful when you have to make improvements on your code, and this might give you an indication where you might want to add changes. And the cool things about this, they are updating automatically. That's really nice. So evaluation of a training is really important, and it is possible to show videos about the different iterations within the notebook as the particles try to find their path without colliding. And this code downloads the generated videos we have seen at the logs folder and display it here also in real life. And you should run this and TensorFlow code after the run started up in order to get the videos and the dashboards also in line. And since these videos are generated about each run, it is really interesting to watch how it improves. The shown video looks really cool. I'm sorry I cannot make it bigger. It's so annoying. I should change this at some point. But we can see that the blue little circles are pretty good at finding their place now. All right. So after this session, I'm going to share this content in my blog with the latest content and the updated code as well. Let me move back to my slides. Because as you can see, when you use reinforcement learning in Azure Machine Learning, you can easily monitor each iteration and see all the training results live while the experiment is running. And if you want to read more, you can see the following resources like blog posts, articles, and some code samples from the engineers or Project Padilla. And if you want to see the game I was just playing, you can find it on the Microsoft Innovation page. And I want to thank you all for your attention. I hope you find this session beneficial when you build your next game. I can't wait to see what you come up with. And also let us know as comments which project would you like to try out the most so we can share some more resources with you. It was a great honor to be one of the speakers of CodeGen, so thank you a lot again for the invitation. I'm not sure if there are any questions at this point, but we are open for questions right now.
Yeah, I don't see any in the chat. Alan, which is your favorite project, by the way? The one that is
that I liked it that every time we hold this session, your rockets are so nicely learning every time. They're like for the second or the third round, they're like pretty good at landing.
Yeah, yeah.
This time you had to restart the whole thing again.
Yeah, I was kind of unlucky with random numbers. That's when you base your demo on random number generation. It doesn't always go as planned. Yeah, I mean that was fun. I found it a bit frustrating to code in Unity with the like the C# Visual Studio implementation. So I've been also moving off to Python more, looking at more Python-based stuff. The stuff that's exciting now is playing around with like the deepfake stuff that they did with the dancing. Like Berkeley did some, you could do deepfake dancing, GPUs. But that's good fun. Takes a long time and a big GPU to train the models though. But that's what I'm currently experimenting with.
Nice. I should make the reward for next time a bit higher for a stop. So what is it called? So the stop requirement, because it is now that I ran it a million times. Now it takes only 1 hour to get there, to reach it. So to make sure that I can show this demo in runtime, so while it's still running, I should maybe make the reward a bit higher.
Yeah.
So if there are no questions, then I don't know.
I have a question. What's your monthly Azure ML bill? How much money is it costing you to run these experiments?
Yeah, it's a really good question. Actually, the Azure Machine Learning Studio itself is not that costly. The computation is costly, and it is based, I mean, the size of it, of course, that is also important. I don't know the numbers by heart, of course, but the compute is really the thing that you should think about when planning a machine learning training like this. And it is a really good practice, and thank you for the reminder to stop the compute when you're done with experimenting, because it is taking money also when you're not using it and it's still running on the background. So it is a very good practice to stop the compute after you're done with your experiment.
Yeah, I've been using the low priority machines, and I found that they're so much cheaper than the regular machines. Also, they seem to be a bit cheaper in the American data centers than the European ones when I've been experimenting. And then when I run my experiments, it's good if it's 3 o'clock in the morning in America, because there's not much demand for the machines, and it seems to be getting them provisioned quite quickly.
Yeah. What other questions sometimes come up?
Yeah, I haven't seen any.
Yeah, we started a bit earlier than 55.
Yeah.
Yeah, well, I guess then I really thank you for having us as speakers today. And I really would be interested if someone starts experimenting around with these projects, and yeah, it would be cool to see what results they get.
Yeah, something I'm going to look at that, because I've been doing all my gaming stuff on premise, and I'm definitely going to explore the options to be able to train in Azure.
Yeah, I was also playing around last time with those Python files, the basic environment to change it a bit, or all these because for example the particle training itself, it has a lot of cool settings that you can change and that possibly improves something. Honestly, I haven't seen much of an improvement yet on that side, but that's when you shouldn't give up, right?
Yeah, absolutely. Yeah, there's always more to explore.
Yeah.